Ready, one, two, three, start. So here we have I have noted some of the major differences between code type and shell type. So it is encouraged that don't write differences like this, that it has two limbs code type and in shell type there are three limbs. Then draw a figure of code type. This is code type, and draw a figure of shell type. You are writing this is code type, shell type. Don't write like this. Write these 4 points. These are the main important points. These are the basic differences between core type and shell type. So the first thing is what? In core type transformer, the windings encloses the limb of the transformer, means the windings are wounded over the limb, and in shell type the limbs are the exterior part, whereas the winding remain as the inside portion. Winding is means the limbs enclose the windings in shell type. Now, because the windings in core type they are the exterior portion, so the second point I have written that any faults occurring, any fault in the winding, it can be easily detected. And since in the cell type the windings remain the interior portion, so faults in the shell type of it, fault taking place in the limbs or in the core can be easily detected. But any fault occurring in the winding cannot be easily detected because it remains inside the winding, inside the limbs, is the core. Third point I have written, since the windings are the exterior portion in the transformer, it can be easily cooled. It means when heat is generated due to transformer operation, when heat is operated, when current is passing through the coil, when heat is operated, ready, one, two, three, start. So the second point I have written that fault in the winding can be easily detected, whereas the fault taking place in the core or the limbs can be easily detected in shell type. So in core type, the windings remain the exterior portion. So that is why I have written any fault taking place in the winding can be easily detected. And since the limbs remain as the exterior portion in cell type, so any fault occurring in the limb can be easily detected. Now, since the windings in core type remain as the exterior portion, so when transformer is operating, when load is increased, heat will be generated. So the heat can be dissipated easily. It means the windings can be easily cooled. So when the windings can be easily cooled, so it gives me an advantage that whenever I will be asked to build a transformer which is of higher current rating, I will choose a core type of transformer. Now, there is a point to understand over here. So, whenever I'll be asked to build or to design a higher current rating transformer, I said what? I will choose a core type of transformer. Now, we need to understand the technicalities behind it. I said what? That when the windings are the exterior portion of the core type transformer, so the windings, due to transformer action, the windings will be heated up whenever load is increased. Winding will be heated up. So if the windings can be easily cooled, it gives me option that I can further increase the load of the transformer because the winding can be easily cooled. But if I choose a shell type of transformer, what will happen? That since the winding in the shell type of transformer remains engraved or it is the interior part of the transformer, the windings cannot be easily cooled. So that is why I have written hence for higher current rating transformers, core type transformer is preferred over shell type. This is an important point. So likewise in shell type, what I have written, in shell type transformer, the limbs are the exterior part. When the limbs are the exterior part, the heat generated in the core can be easily cooled. So I have written hence core can be easily cooled than the windings. So hence for higher voltage rating transformer, shell type is preferred over core type. This is a important point. From here you can get a short type of question also, short type questions, that why we choose a shell type of transformer to build a higher voltage rating transformer. The fourth point is what? The flux path in the core type transformer is from, if you remember, the if we remember the schematic of the transformer, shell type was what? Core type was that flux generally transfers from one limb to flux transfers from one limb to another limb, like this. But in shell type, what happens? In shell type, what happens? The windings remain here, one winding and another winding here. So flux has to pass this limb, the central limb. So the central limb accommodates two flux, one from this limb, another from this limb. So that is why in the shell type, this the flux path for shell type transformer have three different limbs. In the central limb, the total flux from the other two limbs come in and the flux is added up. So the central limb, the two flux gets added up here. Hence, the total area of the central limb is more than the exterior two limbs. Okay. Next. Now, performance and operation of a single phase transformer. The heading is ideal transformer. What will happen if we choose an ideal transformer? So under no load, no load means no load means that it is no output is open, no output current is flowing, output current is zero, output current is zero. Okay. So by electrical, so the same thing is written by electrical load, it meant that output current is zero, no current is coming at the output. So that is why I have written that. So we need to understand that I2 is equals to V2 by impedance. So if I2 is zero, impedance is infinite. So students, please note that output current is zero means impedance is infinite. So infinite means it is open circuit. So what will be the operation? That ideal transformer means windings are made up of copper of infinite conductivity. That means there is no winding resistance. No winding resistance means no voltage drop. So no voltage drop and no power loss, no leakage flux, and no saturation of magnetic core. As long as current will pass, flux will rise and B will increase. B means flux density. So it's very simple. The operation is Vm sin omega t, Im sin omega t. From Im sin omega t, you will get phi m sin omega t. Now, according to transformer action, EMF will be induced. That I have taught that EMF which is induced due to rate of change of flux, that will always lag by an angle of 90 degree. So E1 is phi m sin of omega t minus 90 degree. E2 is phi m sin of omega t minus 90. So here you should note I am writing the nature of EMF. I am writing the nature of EMF, not the magnitude. I am interested to give you the information here that the EMF which is induced is also sine in nature, and both this EMF is lagging by an angle of 90 degree from the reference. So, how to draw the phasor diagram? Now, phasor diagram is always drawn by taking a reference. So here I have taken IM and phi m as the reference. So here I have marked phi m and IM. IM is magnetizing current component. So phi m is generated from IM. So this is taken as reference. Now I have told a number of times that EMF which is induced due to rate of change of flux will always lag by an angle of 90 degree. So both E1 and E2 will lag by an angle of 90 degree. Lagging means clockwise rotation from the reference. This is 90 degree. And since according to Lenge's law, effect will oppose its own cause, so E1 and E2 will oppose V1. So V1 is taken opposite to that of E1 and E2 drawn. So here it is written V1. This minus sign is because of Lenge's law to signify the opposition. So and here in the phasor diagram, see I have written it like this, that E2 is almost equals to V2 because it is ideal transformer and no voltage is means load is zero, nothing is connected in the transformer output side. Output side is open, so whatever voltage is generated at the output side will be equals to E2 and E1 is almost equals to that I have written V1. Now, how I have drawn the phasor diagram that is written over here, that E1 is the current from the source V1, hence I1 produces the flux phi m, useful flux, so that is why it is drawn in phase. According to the nature of EMF, this nature that it is sine of omega t minus pi by 2, so EMF which is induced is drawn clockwise, lagging by an angle of 90 degree. Since E1 is induced EMF, so by Lenge's law, E1 is effect, it will oppose its own cause. So V1 is drawn opposite to that of E1. So at no load, I2 is 0, no voltage drop at output. So V2 is almost equals to E2. Hence, in the phasor diagram, E2 and V2 is shown in the same phasor, and since E2 is also induced EMF, so E2 is also lagging by an angle of 90 degree. So this in short is the phasor diagram of the transformer under no load, ideal transformer under no load. So now why this magnitude, this E1 and E2, this magnitude of E1 and E2 depends on the number of turns N1 and N2. So if N1 is more, it is obvious that E1 will be more, and if N2 is less, E2 will be less, because they are in direct proportion with the number of turns. Means E1 and E2 induced voltage, they depends on the number of turns. If number of turns is more, E1 induced voltage will be more. If N2 is more, E2 induced voltage will be more. So here I am drawing E1, E2 of different magnitude just to signify that N1 is less than N2. So in this figure, N1 is less than N2. Now, so the next class means now on today's class we will start with the ideal transformer under load. Last class we did ideal transformer under no load. Now we will do it under load. Under load means load is connected. So what I have written, when a finite impedance load ZL is connected across the secondary side, now I2 current is flowing in the secondary side. I2 current is flowing. So this difference you have to note. So what is the basic difference between the no load operation to on load operation? The basic difference is I2 comes into picture. I2 comes into picture, but under no load I2 was 0, but now I2 is not 0. So what will be the operation? I have written step by step, try to understand step by step. So whenever I connect a supply voltage V1, I1 current is generated because the primary winding is closed circuit, it is connected. So it will give rise to an I1 current. Now when I1 current passes through N1 number of turns, it produces primary MMF. MMF means ampere turns, ampere multiplied by number of turns. So primary MMF is I1 N1, which produces phi amount of flux in the core. Now what is the function of this flux? This flux links with the primary and secondary coil, and as flux links with primary and secondary coil, so E1 and E2 gets induced. What is the function of EMF? If the circuit is closed, it will generate one current, or it will give rise to one current will flow. Now the point to be noted here is, under no load operation, output was open. So even if the voltage was present, because output was open, current was not flowing, because current always flows in a closed path. So initially, in the previous case, when output was made open, current was not flowing. But here, E2 is induced, circuit is closed, I2 current is now circulating in the secondary coil. What will happen if I2 current is circulating in the secondary coil? Secondary MMF will get generated. Now here there is a problem. What is the problem? N2 I2 is the effect. So according to Lenge's law, so N2 I2 will oppose its own cause. So N2 I2 will oppose N1 I1, means secondary MMF will oppose primary MMF. MMF will oppose one MMF. Voltage will oppose one voltage. Current will oppose one current. Current cannot oppose the MMF, or voltage cannot oppose MMF. So secondary MMF I2 N2 will oppose primary MMF, which is I1 N1. Okay. Now, when this MMF is opposing each other, so we have learned that MMF will be opposing. Now, what will happen if the secondary side load is increasing? Load increasing means current flowing in the secondary side is getting increased. Means if there is a demanding load, more number of loads are utilized, bulb, TV, fridge. To understand the load like this means apparatuses are connected in our household circuit. If we connect too many apparatus, where from the current is coming? Obviously from the transformer side. So if load is increased, I2 current will rise. Now if I2 current rises, what will happen? Secondary MMF I2 into will also rise. This will also rise. Now, if I2 into rises, what will happen? This flux will, means once the flux in the core is, see here I have written that it, see, into I2 will oppose flux. Previously I told what, that N2 I2 secondary MMF will oppose primary MMF. So what is the effect of it? Flux in the core will be opposed. Means flux cannot flow easily. Flux cannot flow inside the core easily. So what will happen? The flux is opposed. Now try to understand. If the flux is opposed means what? Flux will reduce. If the flux reduces, EMF induced will reduce. EMF induced will reduce because EMF induced, EMF is, relation is what? 4.44 phi m F n. This is the relation. So flux is direct proportion with EMF. So here I have written E1 will reduce. So as a result, the opposition to V1 is also reduced. Now here we need to understand a lot of things. So try to understand that secondary side current is flowing now. If secondary current rises, secondary MMF rises. MMF, secondary MMF will oppose primary MMF. So when one MMF is opposing another MMF, what is the impact? The impact is flux in the core is minimized. Means flux in the core cannot flow easily. So if flux in the core is minimized or flux cannot flow easily, it creates a direct impact on the EMF. Why? Flux is directly related with EMF. So EMF gets reduced. Now, if E1 gets reduced, so I have told earlier that E1 and E2 is induced voltage. So these induced voltage will oppose where the supply voltage V1, because here I have taken V1 as the supply voltage. Now when, so due to this, EMF is reduced, flux reduces, EMF reduces. So that means what? The opposition offered by the EMF towards V1 is also now reduced. It means what? V1 is not facing that much opposition which was faced initially. So it means what? V1 is now free to give one extra current in the primary side. So that is why it is written over here. As a result, the opposition to V1 is reduced. So what will happen? V1 opposed less. So as V1 is opposed less, V1 can now drive in more current I1 in the primary side. So this added primary current I1 will generate a more amount of MMF in the primary side in one I1, thus to restore the flux in the core. So here, from here, what do we learn? That whatever may be the operation, the flux in the core does not reduces. I have told you step by step to make you understand the operation, what is going on inside the transformer. So in short, so these actions will take place within a fraction of second. So we will never find a drop in flux in the transformer. Why? Because immediately the primary side will drive one, or it can make extra current to flow. So hence it restores the same value of flux in the core. So flux also remains same in the transformer. Transformer operation, whether it is no load or full load or on load, that the flux, amount of flux flowing in the core is always same. Now we will understand the phasor diagram of the ideal transformer under load, means when load was connected. Now this portion of the phasor diagram, see, the major portion of the phasor diagram remains same as that of the no load. No load phasor diagram was what? I have chosen one reference, IM, and so from IM, phi m gets generated. So IM and phi m is same. The EMF which is induced will be lagging by an angle of 90 degree. Whether I write E1 or E2, these are two induced voltage. So if I make the magnitude different, means the number of turns are different. So opposition was V1. V1, the induced voltage opposes V1. So this is 90 degree lagging. So this was the phasor diagram of the transformer under no load. Now, as I have explained, what is the difference between those two operating condition? Initially, there was no load, means see, I2 is nowhere present in the phasor diagram. But now I have to present I2 in the phasor diagram. So I2, any kind of load, these are mostly inductive load. So I2 will be lagging behind the supply voltage whenever we draw a current flowing through an inductor coil, it lags behind the supply voltage. So I2 is what? I2 is a secondary current. So for I2, which one is acting as a supply voltage? E2, because I2 will get generated from E2, means secondary induced voltage. So I2 will lag behind secondary induced voltage by an angle theta, or it will be not exactly 90 degree, because it is not a pure or loads are not pure inductor, so it is lagging behind an angle theta. Now here I have to understand another thing, that see, when we understood the operating principle of the transformer under no load, under load, that secondary flux was there, secondary flux was opposing primary flux in the core got reduced, E1 got reduced, induced voltage got reduced. So the opposition offered towards V1 got reduced. So V1 is opposed less. So V1 can drive in one extra current. Now these extra current, why? Why V1 is sending one extra current? Because load is rising. Load is rising in the secondary side. Load rising means I2 rising. I2 rising means MMF in the secondary side rising. Secondary MMF will oppose primary MMF. Flux in the core reduces. E1 reduces. So the opposition reduces. So V1 supplies one extra current. So this supply of extra current comes into picture. Why? Because there is a rise in the load. So it means what? Now I have to understand the link between the I2 secondary side current and I1. As there is a rise in demand, load rising, the current is supplied from the primary side. So any demand generated on the secondary side, it has to be supplied from the primary side itself. So that is why whenever we are learning transformer, one thing we should not forget, there is no physical wire connected between primary and secondary side. So it is a magnetically coupled circuit. So that is why any load demand rising in the secondary side means, if the secondary side needs more current, I2 needs more current, it has to be supplied from the primary side. It is not a magic that I will supply, means nowhere is connected. It has to be understood that there is no wire connected between primary and secondary. The entire circuit is magnetically coupled. So any demand generated in the secondary side, it has to be supplied from the primary side. So I2 will oppose I1. So this I1 is the current which is coming from the primary side. Due to, see, if there was no I2, there will be no I1. So the entire transformer remains same as no load. Immediately when it is changed to under load, once I2 comes into picture, that has to be supplied from the primary side, and these two currents will be opposing in nature, because I1 comes into picture due to I2. So according to Lenge's law, I2 and I1 will be opposing each other. So this is the entire phasor diagram of the transformer under ideal transformer under load.